Chapter 3 goes back to quadratic functions, which you spent a lot of time in grade 10, learning all the different types. You may have forgotten a lot of this because you might not have done grade 10 for almost a full year. So let's go over some of the basics, first and second differences, and the types of format. And then in the second video for 3.1, I will do 2 of the more difficult homework assignment questions. So here's an example of some data that you're given. You're given a set, some coordinates. And in order for you to do first and second differences, the x-coordinates have to go up by 1. They can't jump. You can't have just a bunch of different points. Or you can only look at ones where they are only 1 apart. So I check and they do go up by 1s. And then I want to know how does it change from here to here? So there's 2 ways of thinking of this. I can say I went from 15 to 11, so I went down 4. That's one way of doing it. Or the way I like to do it is just once you've listed them, you start with your highest x and you start subtracting. Go the other way. So I'm going to do -1 minus 3, which of course is -4. 3 minus 7 is -4. And 7 minus 11 is -4. Once you've done the first differences, if they are all the same, in this case they are, when first differences are all the same, it means that the function is linear. And if you had graphed this, -2, 15, -1, 11, you would find that it's simply a line with negative slope. It actually has a slope of -4. So it's going to go down something like this, go 0 and 7. So let's say this is 7 here, and it's a line that's coming down like this. Very simple. They didn't ask you to graph it. Usually you use differences just to determine if something is, if your model is a quadratic. Will it fit a quadratic? Will it fit a linear model? And later on, if the third differences are the same, then it would fit a cubic function. So let's look at the second one here. Again, I check. Everything goes up by 1. That's good. And I'm going to do it just my special way. Probably the most common way to do it is just start from the bottom and subtract the number above it, the y's. You don't use the x's, okay? So 7 minus 4 is 3. 4 minus 3 is 1. 3 minus 4 is -1. 4 minus 7 is -3. So I take a look at those. Obviously, they're not the same. It means that I'm going to go ahead and do a second difference to see if they are the same. If they weren't, then it's neither linear or quadratic. 3 minus 1 is 2. 1 minus -1 is 2. And -1 minus minus, remember minus minus means plus, that gives you 2. So this is a quadratic function. The second differences are 2. And that means it would be, because I know it's positive, it means it is concave up. So 2 other little things you need to know. Concave up, like this, concave up. And that is like a cup. So it's concave up past the cup. If you can't make a cup out of it, it's not up. And concave down, why the frown? See, it's very sad. Down, frown, up, cup. Frown and down, up and cup. So that's an easy way for you to remember if something is concave up or down. If I were to sketch this function here, I would have, let's go by 2. So it's -2, 2, 4, 6, 7, -2 and 7, -1 and 4, 0 and 3, and the other ones are absolutely opposite. Across from the axis of symmetry, which you might remember. So there it would be something like that, and you can see that it is in the shape of a cup. Concave up past the cup. So now I'm going to talk about the 3 different formats of a quadratic. The standard form, the factored form, and the vertex form. You probably did a lot of work switching between the types of formats, or you should have in grade 10, so that you could be familiar with each type. And each one of the formats gives you different information about the quadratic. When you're in standard form, and these formulas here are the usual basic equations, sometimes they change letters depending on what textbook you're using, but these will be the ones that you should be most common or familiar with. So here's an example of a quadratic in factored form. Notice that it's like ax squared plus bx plus c. When do you use this format? Well, there's not too much that this tells you, because you have your a is minus 2. So that would tell you, first of all, that it's concave down because it is negative. If a is negative, concave down. It's vertically stretched. The a values are visible in every one of these formats. See a. Very easy. The a tells me that it's vertically stretched by a factor of 2. This came also from, you learned this in transformations in chapter 1. Vertically stretched by a factor of 2. I'm just going to put 2 here. And the other thing that this tells you, this c value, notice there's no c in either of these. The c tells you the y-intercept. Y-intercept. So the y-intercept is 3. So all I know if I was going to sketch this is, well, I could put the y-intercept. Let's say this is 1, 2, 3. The y-intercept would be 3. It's concave down. So I know it's going to go this way, but I don't know where the axis of symmetry is. I don't know where the zeros are. There's so many things I don't know. What you can use this for is finding the zeros using the quadratic formula. You might remember that. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That will give you the zeros, or the x-intercepts for this function. And another really handy little equation, x equals minus b over 2a. I'm hoping you remember that, minus b over 2a, and that tells you where the axis of symmetry is. Axis of symmetry is the line that divides your parabola into 2 equal parts. It's a vertical line. So if I look quickly here, minus b over 2a, that would be minus 3 over minus 3. So b, negative b over 2a. 2a's, 2 times 2 is minus 4. So that means the axis of symmetry would be at x equals 3/4. So if this was 1 here, so 3/4 would give me an axis of symmetry right here. The parabola is concave down. It's vertically stretched by a factor of 2. And remember that when you have a point that's this far, say from the axis of symmetry, another point will be exactly the same distance away from the axis of symmetry, because when you're on the same height, you're the same distance away from the axis of symmetry. So this is going to come up like this. I don't know how high it's going to go, but I could spend time determining that by plugging in 3/4 for my x. I could do f at 3/4 would give me the height of the function here. And I could also find the zeros or x-intercepts by using the quadratic formula, which I'm not going to do right now. The factored form, again, you have your a value. So this would tell me a few things. First of all, that it's concave up because a is positive. Concave up because a is greater than 0. Secondly, that it's vertically stretched again. Vertical stretch, factor of 2. So it's 2 times here. And I know where the zeros are. The zeros, or x-intercepts, are what makes each of these brackets equal to 0. So the x-intercepts are going to be 3 and minus 1. So here's 3. I'm going to do it in a different color because it'll show up better. So I have 3 here. That's 1 x-intercept. Oh, it's not working so well. And minus 1. So there's my x-intercepts. Now the axis of symmetry, remember, is halfway between your x-intercepts. So I guess I'm not up high enough here. Let me slide it up a bit for you. Okay, so the axis of symmetry is halfway between the x-intercepts. So you could do -1 plus 3 would be 2, divided by 2 is 1. So when x is 1, that's where your axis of symmetry is going to be. So I'm just going to put a little dotted line here. So that would be x equals 1 is your axis of symmetry. It's concave up. If I wanted to know how far down this function goes, if I want to know where the vertex is, so I'm just going to write vertex here in nice purple. Vertex, I'm going to have to figure out what is the height of the function when x is 1, or solve for f at 1. So 2 times 1 minus 3 times 1 plus 1. That's going to be -2 times 2 is -4 times 2 is -8. So that means the vertex is going to be -1 and, +1. -1 was a 0. So vertex is 1 and -8. So 1 and -8. That's going to be right there. So I can make a really good sketch of this one. I have lots of information. It's going to go down like this, back up like that. It's concave up. Everything is good. The last function I'm going to do in this lesson is a vertex form. The vertex form, h and k give you the vertex. So in this case, the vertex is going to be at, remember x's are weird, looks like 2, but it's -2, but it's going to be +2 and 4. That's my vertex. So down here I have 2 and 4. Is it concave up or down? It's concave up. Vertically stretched by a factor of 3. Now the vertex form gives you all the transformations. Vertically stretched, factor of 3. And so that's vertically stretched, shifted right 2 and up 4. So right 2, up 4, that gives me my vertex. Now if I wanted another point on this, and because it's a vertex, it's also where the axis of symmetry is going to be. It goes through the vertex. So x equals 2 is the axis of symmetry. And another good point to have to give me a good sketch here would be to find the y-intercept. How do you find a y-intercept? You set x equal to 0. So I'm going to find out what is f at 0. So I'm saying, what will the height of the function be when x is 0? So I plug in a 0 here. 0 minus 2 is -2 squared is +4 times 3 is 12 plus 4 is 16. F at 0 equals 16. So 4, I did 2, 4, 6, 8, 10, 12, 14, 16, way up here. So that means my vertex is going to be way up here. Sorry, my f at 0 is 16. That's here. Here's my axis of symmetry. So that means that the other point is going to be the same distance away from this axis of symmetry, and my graph is going to look like this. Notice how stretched this function looks. Okay, so that's the first part of 3.1. I'm going to do questions 7 and 11 from your homework. You might want to take a look at those, and that will be in the second lesson for 3.1.